So good afternoon, everyone. So I'm also a radar guy. So I'm very happy to talk about our phase array radar system. Okay. Okay. So today I'd like to have a talk on the advantage and disadvantage of the phase array radar system. So as you may know, first phase array radar system was developed by Osaka University and Toshiba Corporation in 2012. So as you can see from these movies, this radar system has electronic scanning for elevation and mechanical scanning for azimuth. So however, this is a single polarimetric radar system. So after that, in 2017, 2 years ago, we have developed a dual polarimetric phase array radar system and installed that system in Tokyo metropolitan area to demonstrate at the Tokyo Olympic Games next year. So in both radar system, we have we make use of digital beamforming technique. So if you look at the parabolic type conventional radar system, they transmit pencil beam like this. So that means this radar system mechanically scanning in both in elevation and azimuth. And the parabolic antenna goes around in a certain elevation angle. So on the other hand, in case of phase array radar system, we transmit fan beam into the air. And so after that, so at the digital signal processing stage, we narrow the beam into just 1 degree. So that is the basic concept of the phase array radar system which we developed. So in such a way, for example, this is a horizontal distribution of radar reflectivity, doppler velocity, ZDR, phi dp, kdp, and rho hb. So these images, three-dimensional images, are updated in just 30 seconds. So this is a kind of demonstration, animation of real observed data set for horizontal reflectivity, horizontal doppler velocity, ZDR, and rho hb. So this is very impressive. So, however, we have some problem with this radar system. So if you look at here, the left one means the, under the clear sky conditions, and the right one is the under the rainy conditions. So here you can see some very scattered and very strong ground clutter, basically which comes from the tall building in Tokyo or Osaka downtown area. And also, if you look at the phi dp dual polarimetric variable like phi dp or kdp, something like that. So also, this is under clear sky condition, and this is the rainy conditions. So you still have some problem with even in the dual polarimetric variables. So the advantage and disadvantage of the phase array radar system is listed here. Of course, phase array radar system has a big advantage of fast scanning and dense observation, which leads to the early and accurate warning. So, however, because of the digital beamforming technique, so we have strong ground clutter contaminations. So this kind of contamination leads to the ghost precipitation when you apply the in the data assimilation. So my question is, how can we reduce this disadvantage? So what is the actual problem in phase array radar system? So actually the problem is here. The two-way beam pattern is poor. So I said in digital beamforming technique, we transmit fan beam. That means the main beam is very fat. So because of that, also the side lobe is also high. So the two-way beam pattern, the side lobe, peak side lobe level of the two-way beam pattern is minus 13.6 dB, which is higher than the conventional parabolic type radar system. So this kind of this causes the strong ground clutter in our radar system. So my proposal in this study, so a new beamforming technique using the minimal mean square error formation has proposed and tested. So in this formulation, here is the signal processing in phasor radar system. So in this case, the X means the reflectivity at each direction of arrival. So in this case, Y is the received signal. So with this, received signal is linearly correlated with the radar reflectivity like this. So in the phasor radar signal processing, the beamforming is to calculate the weighting average of received signal in each element and to calculate an optimal weight. So in the conventional phasor radar system, usually they take a Fourier method. That means the weighting factor is equal to in all the antenna elements like this. So, however, in this study, so weighting factor is calculated by minimizing the residuals defined as the difference between the reference and the weighting average of the received signal like this. So cost function is here. So in order to preserve the power in main lobe, so we attach this term additionally. And the solution is here. So however, we still have unknown parameters. So in order to have the actual solutions, so we input the initial value from the solution of beamforming method. And then after that, so we calculate the weighting factor like this. So this process repeated until we have a stable solution. So in this way, well, this is a numerical, the result of the numerical simulations. Well, okay, so this is elevation and this is amplitude. So in this case, the black is the truth. So here you can see large peak. That is a signal from ground, and this slope means echo from precipitation. So if you take the conventional Fourier method, which is in blue, so because of the very, very strong ground clutter, which mask the weak precipitation echo here. So however, if you use this type of MMSE method, so you can see which is in red, you can see we can actually extract the signal from weak precipitation and strong echo from ground itself as well. So in such a way, so this is the actual result. So if you look at here, this is a horizontal distribution from at the elevation angle of 0. That is just above the ground. So you can see very, very strong signal from a tall building in Osaka downtown area. But however, if you go up to the 5 degrees, this is above the tall building. So you still have some ground clutter. This is a ghost echo. So if you apply this MMSE method, even if in the elevation angle more than 5 degrees, G's strong ground clutter is cancelled significantly. And also, if you look at the vertical distribution of reflectivity factor, so this is a clear sky conditions. So you can see a very, very strong signal from above the tall building. So if you apply the MMSE method, so you can see all the ground clutter was cancelled significantly. So maybe this method works very well, probably work well. And so, and also this method can be applied to the doppler processing in the phasor radar system. So if you apply this, for example, even if you have even if in the elevation angle of 0, so all the strong ground clutter was cancelled. That means phasor radar system does not have any contamination from ground clutter. So in that sense, phasor radar system is superior than the conventional parabolic type radars. So here is a summary. Of course, phasor radar system has rapid scanning and dense observation capabilities. So, but it also has the advantage of observing without any ground clutter. So probably the only drawback will be a cost. So that's all. Thank you today.